and you come back, the distance, your position now in a sense is x plus L, right? But that's to equal x again. Okay, so you got the kind of cyclic condition. The value of x is the same as x plus L. You could imagine specifying your position on the circle by an angle, and if you rotate by 2 pi, you just get the same position, right? So it's sort of equivalent. Okay, now using this trick, and I say it's a bit dicey physically, what does it mean? But anyway, mathematically it works. So you're now integrating the probability density, right? Psi is your psi function, squared gives you probability density. But now it's not between minus infinity and infinity, it's just say between 0 and L your circumference, and that's to give you 1. So that means your psi function for your free particle, here's now your normalization constant, right? And it works out to be 1 over square root of L. Okay. Right, it's the square root of L. Do that for homework. You're seeing this HW regularly now. As we get more and more into the course, more and more derivations, which I ask you to do for homework. Okay. So anyway, this wave here, it's called like a running wave rather than a standing wave. A standing wave has 0 values at fixed positions, like when you attach a rope to a wall and you sort of wiggle it like this. It'll get into a standing wave pattern. There'll be certain positions on the rope where the amplitude is just 0. Right? So this is kind of running wave. Okay. Now, so in a sense, running in a circle. Okay. Now, so just contrasting here the difference between, say, a running wave and a stationary wave. All right. Now, this idea, even though it might seem a little far-fetched physically, it has mathematical consequences. Now, look, you've got here your wave function now normalized. So here's your constant such that when you normalize it, you do get 1. So it's 1 over square root of L. So take this waveform here and put this condition in it. Now remember me saying a bit before that x plus L should be the same as x. So you want your wave function to be single valued, the same value, at these 2 positions, at x and x plus L, right? Well, if you put x plus L here for your x here, and psi of x plus L should equal psi of x, then this e to the I kx implies this. I hope that's fairly obvious to you, right? So maybe I put a homework for that as well. It's fairly trivial, but anyway. So that implies that e to the I k big L is 1. Okay? For this condition to be true. So now for that to be true, then k has to be some multiple, integer multiple of 2 pi over L. All right? Okay, and n can be any integer, like z. Well, if you followed me in the previous course on finite groups, which was a math course, z here is the set of all integers. In other words, 0, plus or minus 1, plus or minus 2, plus or minus 3. So I've got the sniffles a little, I think from the air conditioning. Just a minute, I need to blow my nose. Okay. So n here is an integer, right? Now this is a free wave, so we're not stationary. Now as n goes very large, then for large L, then the differences in the now it's still discrete, right? N's an integer, so k here is not continuous, right? It's k is discrete, so this k here is discrete. So your wave functions are discrete, right? But with the correspondence principle again. As n goes large, the differences between the momenta and energies get very small, right? Until in the limit, as n goes very large, you pretty well get like the continuous case. You know, the differences in energy levels and momentum levels are so tiny that effectively it's continuous, right? Now let's jump a little and move from the one-dimensional case that we've been doing. Nearly tripping over the bed there. So here's your one-dimensional case. We're talking x, just in one dimension. But let's start talking now a bit about the three-dimensional case. Now instead of having just like kx as before, now we've got k vector dot r vector. Now dot as in the scalar product of two vectors. Now that's from linear algebra. I will be teaching a course on linear algebra at undergrad level because it's so important. But I assume you've done enough undergrad math and physics to know what a dot product is. Now k before, k here, remember just the wave number, by definition 2 pi divided by lambda, and lambda is the wavelength, well your de Broglie wavelength of the wavehicle. The wavehicle's wavelength. Okay, 2 pi over lambda. And here it's just a scalar, right? Well here, the little wiggle underneath makes it a vector. You know, a vector is a scalar with a direction. Now what is the direction? Well, it's if you, for example, imagine my arm here is the wave front, you know, the front of the wave. And imagine this wave is heading in that direction. Well, then the direction of your k here would be that direction, sort of like 90 degrees to the plane. So imagine this is the plane of the wave, and the wave's heading out that way. So the direction of your k would be that way, and its value, well, that would just be the same as, you know, the wavelength. Okay. And r, well, that's just an ordinary position vector. It's just you know, x, y, z, you know, the three components of your position, and that's just the same, right? Well, now this is one of the downsides of this new method. I now have to switch off the camera, so that will be, well, yeah, assuming this is successful for a while until the next innovation, whatever it is. This will be the new routine.